Good morning, everyone, and welcome to the 36th ETP4HPC webinar. I am Pascal, ETP4HPC's Communication Manager, and my colleague Gabriela is also here to help run the show. For those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC. And we are a private member of the EuroHPC-JU, and our role is to propose research priorities for Europe in the area of HPC, of course. And well, that's exactly what we are going to talk about today, about research priorities in two areas today, storage and I/O and programming environment. So before we delve into today's subject, I have some practical information to share with you. This webinar is recorded and you will receive the link to the recording tomorrow. This webinar is in listen-only mode, but you can exchange with us. If you want to ask questions, you can use the question tool, and you can also download handouts directly from this session. There are 5 handouts for you today, the slides, of course, and also the white papers we are going to talk about today, and the SRA 6 itself. So feel free to download those documents. Feel free to submit questions at any time during the presentation, but we will handle them at the end of the webinar, and we will display the questions in the chat. So, yeah, I had a special word of welcome today. We are welcoming the participants from Castiel 2 and from the EuroCC in our webinar. We have collaborations with them, and we are really very happy to have them on board. So, hello, really. And we hope to have you on board for many more ETP4HPC webinars. So let's welcome our speakers today. Today we're welcoming, well, I'll start by the end by Sai, because he's our SRA leader. So Sai is here, of course. He will introduce the webinar and help answer your questions if needed. But our 2 guest speakers today are Philippe Deniel from CA and Paul Carpenter from BSc. So thank you, Philippe. Thank you, Paul, for being here today. Philippe can't switch his camera on today, so apologies for this, but I guess many of you know him already. So I will hand over to Sai to say a word about the SRA 6 and present the agenda.
Yeah, thank you, Pascal. Good morning, everyone. Nice to see all the attendees. So just a quick summary of SRA 6, as many of you know. So the SRA 6 is meant to be the go-to document to capture the state of advanced computing technology and innovation in Europe. And we target the general community as well as our HPC decision makers and funding agencies. So for the SRA 6, we have in total 9 research domains, so-called research domains, which are different technical areas within HPC, and 3 thematic trends. So for the research domains, last time we had the system architecture talk, for example, and we have others. Just to give you an idea of the research domains, we have system architecture, system hardware components, non-conventional architectures, system software, programming environments, I/O and storage, HPC usage, maths and algorithms, and ecosystem technologies. So those are the research domains. And for the thematic trends, we have quantum plus HPC, energy efficiency, and AI and foundational models. So today, my colleagues here, Paul and Philippe, they're going to focus more on the programming environment and I/O and storage side of things. Hopefully, it's going to be interesting for you, and we look forward to questions and comments from you all. Yeah, that's it from my side. Pascal, back to you.
Yeah, sorry, I just realized there is an error in the timing on the agenda. Our speakers have 20 minutes each. So copy paste error. I'm sorry.
Well, you just about my time.
Okay. Okay, so I think we can now hand over to Philippe. Philippe, I will make you presenter so you can
Yeah.
share your slides.
Okay. Okay. So I'm very clumsy with this kind of interface. I hope this
No
will work.
problem. We're between friends, so we're only 30 people here.
Okay. Can you see my? Yeah. Maybe I'll be
Yeah.
switching
Can you
to
go in
slideshow
full
mode. It will
screen
be
mode?
better. Yeah. Is it better this way?
Perfect. Perfect.
Okay.
Yes.
So hello everyone. So during the next 20 minutes, I'll be exposing the SRA 6 work regarding I/O and storage. So this action has been done by a group of 10 people, led by Sai Narasimhamurthy and myself. And so the list of people is currently displayed on the screen. And thank you very much to every contributor. Since we had lots of interaction and lots of fruitful discussion, which led to this Series 6 document. Okay, so let's first have a look at the big picture. Basically, this document, this SRA 6, is a follow-up of the SRA 5 document, and particularly the I/O document, which was written in 2020. I/O and storage are a critical part of HPC. Basically, HPC is we can consider it as massive supercomputer performing lots of computation, I/O storage system, and high bandwidth network in between them. In a very, very stratospheric point of view, this is the way you can draw the big picture of an HPC center. As we come to the exascale, we'll be facing new challenges which were not existing at the time of petascale or terascale. We have to deal with classical, would say, data scalability and associated metadata scalability. For metadata is going a lot as well.
Philippe,
And yeah,
sorry to interrupt. So there's a small, we see this panel on your screen
yeah,
as
me
well.
too. I thought you did not see it.
Okay, so
Yeah,
if there is a way to,
it's a bit buggy actually.
now it's, yeah,
Yeah, so it disappeared. So that
now it's good.
do you
Yes.
see it?
Yes, perfect, perfect. Thank you.
Yes,
Go ahead, Philippe. Sorry.
since I upgraded my workstation to Fedora 14, the Evans this PDF displayer is behaving weirdly.
No
Okay,
problem. It's good now.
so data scalability is the first challenge to cope with. I'll have to handle up to exabyte or tens of exabyte too. So it's massive amount of data. And at the same time, the metadata will grow a lot, and we expect metadata to grow up to 10 to 15 or 20 terabytes, which are quite large. And we'll have to have specific methods to handle those large amount of data. At the same time, we have the classical system scalability issue, where the number of clients will grow, and you have to deal with the pressure of this larger number of clients, resulting in larger connection to the system, which we'll have to find way to deal with this and to reduce the pressure on storage system, including pressure resulting from the network. CPU and GPU evolution is something more tricky, and it's quite a kind of new problem. The fact is, GPU brings lots of core inside a single node, and it will bring hundreds of core inside a node. And if you look at the evolution of the available number of core in a node and compare it to the evolution of the RAM, of the memory, you will see that the number of core evolve more quickly than the memory itself. Memory is growing, but not as fast as the number of core provided by many core CPUs and GPU mostly. So the memory per core ratio is changing in the wrong way, which means that if you run a simulation code, usually it requires an atomic amount of memory, such as 2 gigabytes or 10 gigabytes of memory per core. And the more core you have, the less memory remains for running system software. which make some of the classically evolved algorithms, such as distributed lock manager, for example, much more difficult to implement as we come to the exascale. We have to deal now with deep storage tiers involving NVMe, involving SSD of different class, involving rotating disk, HDDs, involving tapes, and it's very different from the good old time when we just have to deal with tapes and rotating disks. And it's this deep hierarchies with very different hardware characteristics makes it necessary to place and locate the data at the right place as soon as possible. You don't want to have your checkpoint restart file to be stored in the expensive NVMe disk. You want it to have them on tapes. And next but not least, we face a large variety of use cases leading to strong data heterogeneity. Different kind of files, different kind of workload, different kind of storage usage, and you have to build a storage system which is able to cope with all of these different aspects. We wanted to announce the AI use case, which is really very important. There is a strong engagement in the industry, and sometimes you have supercomputer dedicated to AI, and it seems necessary for the SRA 6 IO and storage work groups to have a specific focus on it, which you will find this in the in the associated white paper. So I'll be fast on this slides in order not to explode my schedule time. So basically, on the right-hand side, on the left-hand side, you have the classical supercomputer structure. So you have a parallel file system and MPI stuff. But if you move to the right-hand side, you enter the cloud storage area, when you have object store and at the mid and both word HPC and cloud storage, they tend to mix and hybridate themselves by sharing technologies. On the most significant one is object store, which and you have some applications such as TensorFlow, for example, which are able to cope with object store as well as parallel file system. And object store do exist in HPC. For example, you have DAOs, which is kind of an object store as well. And the two words tend to converge and to hybridate themselves by providing common method. Of course, we will not be able to fully merge HPC and cloud storage, for they are very, very different animals, but there will be some area of convergence. Okay, so let's have a focus on the research on that were identified in the interesting domain of research that were identified by the work group. So the first is middleware and IO subsystem integration. So we have those exposed challenges, and we need to perform efficient to provide efficient software to deal with them. So the first of it is data scalability, and of course, we want to store many data and we want to access them quickly. So what is important is having a deep knowledge of the data path of the involved storage medium, including the RAM, including the efficient NVMe or the very capacitive tapes, and identify the bottleneck as much as possible in order to give efficient solution to the end users. This can be done by integrating emerging technologies. So NVMe is part of it, object store is part of it, but at the same time, this emerging technology brings new challenges and require to develop new solutions within the middleware. As you involve more and more subsystem, more and more disk, more and more tapes, more and more devices, more and more servers, server nodes, you have a risk of an higher risk of failure, which means that you need to make an additional effort regarding reliability and fault tolerance. And we need to have a nice tool to deal with them. And we know that no tool will be able to deal with everything. If you're looking at an NVMe device, then it's quite easy to make checksum on it. They have a very low very fast bandwidth, so you can perform checksumming very, very easily. But you won't duplicate the data for the NVMe device, are very expensive. On the other side, if you're working with tape, you will not perform checksum. It's too slow, but it's very easy as you write data to write the data on two tapes at the same time. For this is quite inexpensive. So we have to leverage the characteristics and benefits of every storage subsystem to handle that. Energy efficiency is quite important. Systems are becoming larger and larger, and we don't want to have to build a nuclear plant next to every compute center in order to power it. It's something we can do, so we have to think about energy efficiency, which makes tape very, very interesting. For tapes do not consume power as you do not use it. They are very passive devices. Computational storage, which is basically computing on the storage device, is an interesting paradigm for it prevents from moving data, and it saves some. It can prevent some bottlenecks to occur, and it's very similar to edge computing. For example, you can imagine you have a neural network running on a storage device. It's trained on the HPC system and moved on the characteristic on the neural network are moved to the storage server, which has some small CPU to run it. And so we can perform simple transformation of the data directly on the storage devices. Data transfer is very important. So moving data across data center is very complicated. Sometimes if you have to move tens of petabytes, sometimes it's not easy to do it over the network. You may consider to put all your tapes into a truck and send the truck on the highway. Sometimes it provides you with a better bandwidth. So, but on the other side, as users are often spread across multiple compute centers, they compute in different places and they want the data to be in those places, which requires the data to be replicated across multiple places, which may require some dedicated asynchronous tool in order to replicate and version all of the data sets to be used by the user on different places. And this leads to challenges on authentication and user access. And we want the storage devices on storage system to have all of the authentication tool and method in order to identify the user and to allow access to the right data set for the right person, which is done by automated data management tool and metadata catalog, including different versions of the data to do that. And as of course, this data aspect, as I said earlier, you need to put the right data at the right place. You need to deal with that data heterogeneity, and you don't want the data to move for no reason, for bad reason. As much as possible, you have to characterize your data and put them at the right level of storage as fast as possible. This led to the question of multi-tier systems. So with a multi-tier system, you sediment. You have your. I used to say you sedimentate. Maybe it's a very dirty Gallicism. Sorry for that. But you have your data moving down to the storage tier as they become colder and colder as they are less used. We have to have nice policy, which are able to put the data at the right place, and we think about using machine learning to identify the data that move the less, in order to put them on cold devices, on tapes, and identify the very hot data which are frequently accessed and keep them on the hottest storage devices as much as possible. Object Store is a very interesting service for its scale as well, and it will answer some of the challenges provided by Exascale, and it makes a de facto bridge with cloud technology. Since the system open to the world, we have to consider cybersecurity, so authentication, of course, encryption if we want to protect your data, encryption which can be different regarding the storage devices. You definitely want to encrypt the data the same way on tapes on NVMe. If users may access the same data via HPC file system interface and cloud storage, and we have to deal with that multiple access pattern having different bridges with different protocol to access the same data sets. Ransomware is something which is an actual risk, and we have to cope with it. We have to maybe have backups, have several copies of the same data, have several versions of the same data in order to protect the HPC center against ransomware. In order to prevent that kind of attack, we have to detect suspicious activity. For example, you may look at the user's behavior, and if it's suddenly getting interested in the /etc directory, it's very strange. And this kind of suspicious activities could be detected even by machine learning. And this is done as well by some methods, including auditability, versatility, and agility. The more we move to exascale, the more we have a very polymorphic end users. We'll have end users performing raw physics, some end users making interactive computation, maybe via something like a Jupyter Hub stuff. And we have to deal with this interoperability and be sure that we have the right data made available for the user at the right place with the right performance. So we have to know what the users will do and make it able to put the data at the right system, at the right disk, at the right storage system, in order to provide the user with the most optimal user experience. So this is an array from the SRA document, so I will not comment it, for it's very dense. But it's very interesting for it takes different challenges and the available solution, and it depicts how each of the problems of the challenges can be addressed by a new by some of the research trends. So we are not we have weapons to cope with those challenges. We have ways to address them, and this is what this table depicts. I'll be quite a bit fast about exascale vision, but basically we can say that there will be evolution within the compute center. So you have this before-after picture, while you have addition of new devices such as very, very fast devices, probably devices even faster than what we have in NVMe. And we have something that may come on the other side, which is DNA storage, which I used to say that it's like quantum computing was for HPC. Everybody thought it was a funny thing, but won't occur. On one day, quantum computing became a reality. On one day, DNA storage will become a reality and will provide massive, but very slow, but very reliable storage for HPC center, and we'll have to handle it. Post-exascale vision include hyperconverged infrastructure in which you have a single box managing software, storage, and networks. And this requires blurring the line between storage system and the network, making the storage system aware of the network behavior, for example, detecting congestion, detecting bottlenecks, making transfer via different routes when available, and making the network knowing that being not agnostic of the system, knowing it's connecting to a storage system or connecting to an HPC system, and adapt its routing methods, for example, for that. Computational software is part of the exascale vision. I already talked about it. In order to deal nicely with the system, we need to know precisely how it's working, so we know precise monitoring at every step, and analyze the collected data, which can be quite large, with all available tool, which includes the AI. And AI may be quite interesting in many exposed fields, such as detecting suspicious behaviors, such as automated data placement, and this kind of stuff. Power consumption is a vital point of view. It's very important. On data gravity, which is basically moving data across a deep tier and placing the data at the right location. So it's kind of a word. Gathering all of these aspects is very, very important. This led to the recommendation. So we need to have a deep knowledge of the I/O, the data pressures, the I/O patterns, and we may use AI to monitor to analyze that. We need to handle object store and make it interoperable with file systems and having a convergence between the HPC cloud and the object store, the HPC system world. So, and I really believe that object storage is a key technology for exascale. We will not will continue being a parallel file system, but there will be a big part of data being stored on object store for this scale very nicely to the exascale. Data placement or energy efficiency are two sides of the same coin, basically. If you place the data at the right location, if you don't have to move it, then you do not spend energy to move it. And it's so we need to have a nice data placement, an efficient and effortless way of moving data. Fault tolerance is very important to prevent from corruption, classical hardware production. Basically, you have a failed disk, you have a corrupted tape, and to prevent from nasty people, basically ransomware and cyber attacks. We have to think about computational storage, which is a way to if your data is well placed to save energy, for you don't have to move the data if you can manage it directly on the storage system. You have to do all of that via middleware and new tools, including data transfer tools, which will include security and new authentication mechanism. And we have to have kind of unified authentication mechanism, which at the same time resonates with cloud technology. For access to cloud is an authentication to cloud is very, very important. And if you have connected to Amazon Azure, or any other cloud provider, you're aware on the way you have to authenticate to this kind of stuff. And as you transfer data, they can be taken by other people, so you may need to encrypt your data on the path. And last but not least, everything has to be integrating into a workflow and be managed by specific tools. And that's all for me.
Thank you. Sorry.
I think.
Thank you, Philippe.
Yeah.
Yes, you're in. Thank you very much. You're perfectly on time. So I will allow Paul to share his slides, and while Paul is sharing his slides, I'll remind everyone that we will take your questions at the end in the question tool. So you can ask them whenever you want, but we will answer them at the end. Paul, are you ready? It looks
Yes,
like
I'm
you
ready.
are.
Do you hear me?
Okay.
Do you hear me?
Thank you. The floor is yours.
Okay, thanks, Gabrielle. Good morning. I'm Paul Carpenter from BSc Barcelona, and I'm going to present the programming environments. So this was done with my co-lead Gabrielle Antonio and the working group contributors who are listed here, and we also had very good discussions amongst the working group and a lot of collaboration here. And more details, of course, on everything I'm going to say is in the white paper that's available. So, introduction and state of the art. I think somebody's got their microphone on. I heard something. Anyway, we have 4 main themes. So one is programming with parallel languages. So of course, mainstream in HPC at the moment is Fortran or C++, plus OpenMP, CUDA, MPI as a communication API. There's some take up maybe in the US from Kokos and Raha, and a little bit from SYCL. But as we've said, actually, since the very beginning of ETP, this is something, a topic that has had constant research, but it's still true that current approaches do require deep understanding of the hardware architecture, which conflicts with any kind of idea of portability. More recently, there's been adoption of heterogeneous and hybrid memories. I'll talk more about this, which are a special challenge. So that's the first. The second, I think, is very clear. Of course, we've mentioned AI in SRA 5, but then a couple of months after publication of SRA 5 was, of course, ChatGPT, and amazing progress, as everybody knows, in the AI space. It's worth pointing out that HPC techniques do underpin a lot of AI training, linear algebra libraries, low latency communication and synchronization. So HPC has really contributed. But anyway, looking at the programming environment, there's really 4 ways in which this can really have an effect on programming environment. So first, we see more and more HPC workloads incorporate AI as part of the workload itself. That's one thing. Second, things like ChatGPT and so on, generative AI, maybe more interesting things, can assist in the software development process, including for HPC. Then AI techniques can help with code optimizations, runtime optimizations, and also something to be aware of is that as the broader market prioritizes AI in terms of architectures and so on, some of the things that we rely on from HPC may get neglected. I'll point to some of the more obvious things later. That's another thing. Task level programming. So task level programming kind of became mainstream in HPC with OpenMP3, which was 2018, something like that, a few years back. So it's mainstream in HPC. There's a very good European ecosystem, StarPU, OMPS, of course, and BSC, and others that have contributed also to standardization of OpenMP. But adopting tasks, I've been in projects, and from the programmer's, designer's point of view, it seems fairly simple, but from the point of view of a very large, complex application, it can need some in-depth thinking, so rethinking. So this is something that needs to be taken into account, and also means that the application owner has to really trust that there's going to be high quality long-term support from the programming model side. That's the third point. The fourth point is malleability. So traditionally, of course, in HPC, we have a block of n nodes with a time limit, and the resource utilization is constant throughout the job. Malleability is a general topic of dynamic resource management, generally to improve system utilization energy, maybe also to support interactive and urgent computing. This topic involves resource management, program environments, applications. I'll say more about this one also, because but at the moment, the support is relatively limited on the programming environment side. So then going through the challenges, related to the increasing share of AI workloads in HPC, we see more use of Python, we see more use of containers and container orchestration, that this needs to be dealt with well in the programming environment. The greater convergence between, so cloud systems start to adopt, say, accelerators and better performing networks. So there's more similarity between cloud and HPC systems. The point I said about prioritizing things for AI, you see, for instance, Blackwell now has down to FP4 very famously, and Int4. So making use of this becoming available means mixed precision algorithms, libraries, tools to help with finding the right trade-off between precision, or at least precision and quality, or the lowest precision to get the target quality. And then the importance of interoperability between HPC and AI environments. So you get many of the issues that you get with interoperability in general in terms of data conversion between different frameworks, usage of resources like cache and memory, resource management like cores and so on, when you have the different environments at the same time. Another topic, AI at the service of HPC. So there's been some work. DeepMind found new matrix multiply algorithms from using machine learning AI techniques, Alpha Tensor. There's also some work from Oak Ridge on AI to optimize to optimize BLAS. This can be broadened to more kernels, maybe even, I can't spell, it seems, integrating some of these techniques into the compiler flow even. Looking at the whole program, good question is to what extent can LLMs generate efficient parallel code, given the smallish amount of training data in HPC compared with the rest of the world, and the complexity of this kind of thing. Also interesting is using techniques for refactorization, or again, I can't spell, modernization to newer versions of Fortran, or to from Fortran to SQL and so on. Another thing I find very interesting is a natural language interface to some of these tools that can be quite idiosyncratic and quite, technical. Performance and debugging tools. Be nice to have natural language interfaces to use them. So then programming with HPC. I said briefly before, we all know HPC applications are complex, very long lifetime. We would like the application to be independent of the specific resources that are available. Task-based models can help with this. A very simple example would be, say, using a task loop and letting the runtime choose the grain size rather than you dividing it up, or querying how many cores there are and dividing it up by the cores. There's a lot of interest in programmer productivity, which I think is a great goal. It's definitely a goal that we need, but it is actually difficult to quantify what we mean by productivity. There's some metrics available in the literature that maybe are more targeted towards writing code rather than porting them, maybe are not really appropriate for parallel code. Recent-ish projects, EPEAK, prioritized qualitative analysis and getting feedback from hackathons, but something quantitative would be very good, and that definitely needs, it definitely is a challenge. Another challenge is, I mentioned the heterogeneous memory before, which is of course already a reality. There's been a couple of discontinued things like Knight's Landing and Octane and so on, but then Sapphire Rapids, of course, supports DRAM and HBM. CXL is also very exciting, and then there's accelerator memories, PIM, near memory computing. And I think more work is needed on the ability for programmer to provide hints, and maybe some combination. You can deal with data placement and migration in the programming environment, in the operating system based on page hits and so on at the page level, and maybe in the hardware. And they have maybe different pros and cons, and some combination can be an interesting approach. Then we talk about interoperability, composability, and standardization. So these have been mentioned several times, but I think it's interesting to distinguish between, at least here, interoperability, meaning the same programmer language abstraction or programmer level abstraction can be used across all of the tools. And the big challenge here is you write in something high-ish level. You see this even with C++ errors, at least without concepts, where you get massive, because there's such a massive gap between the things written in the source code and what's actually happening in the low level. And that's quite a challenge to convert things into a way that people can understand. Composability is about combining multiple programming models with defined rules, reusing fragments from different programming environments and so on. And I mentioned standardization before being super critical for the take up of any kind of programming environment techniques in production applications, because standardization, whether it's formal or de facto, can help ensure long-term availability and good efficiency across a wide range of systems, vendor support, and vendor neutrality, which you really need if you want to, for real, adopt something in applications. Then we have a number of challenges related to the computing continuum. Computing continuum being use of HPC, edge, cloud within the same workflow. If you have decentralized kind of workflow and no kind of master and control, you need these resources to work together. You need resource allocation when you have very different kinds of resources, programming models that can abstract in a good way to allow tasks or whatever your granularity of work is to adapt and run efficiently on the cloud, on the HPC, on the edge. Volatility and instability mean resilience is important. The resource allocation needs to take into account the heterogeneity. In some applications, such as federated learning, if you have divergence across space, across different things, you need to cope with that. Obviously, security, cybersecurity, encryption, and so on, privacy, important. If something's distributed, then data consistency, data scalability, and data availability are important, especially because you want to reduce or minimize the bandwidth and energy consumption. Depending on the application, different latency, different locations may have different latency characteristics, so you have to deal with that. And of course, energy efficiency. For these computing continuum applications which use or which consume enormous amount of data, you need interoperability between the different parts, the simulation, analytics, machine learning, and to run workflows that collect data from instruments, do processing, and so on. And a point that's made in the document is at the moment, these systems tend to concentrate on task flow control, and more emphasis can be put on the data management in addition to the task flow control. Another topic I mentioned at the beginning was the malleability. There has been a lot of very good progress in recent projects, such as DeepSea, Admire, Timex, Regal, EU Pilot, that are focused on support for malleability at the lower levels. So actually, as it says there, MPI has supported dynamic processes since very early, but I've tried using it, and there are some issues with the way that the API is defined that kind of get you into trouble. And because nobody uses it, the support can be kind of buggy and not really very strong support. So dealing with this first has been really important. MPI 4 sessions is very important as a way to enable that. The resource management and the scheduler, that's where much of the work has been recently advanced. But at the programmer level, there's still more to be done. The interfaces tend to be different from the different projects. And now is the time, I think, to start working more on the programming environment. To interact with the external environment means essentially the batch scheduler. The big problem, dynamic resources maybe is one thing, but the important aspect is the data redistribution. So are you on your own, or do you get some help from the programming environment? And again, with the interaction from the external environments, this should take account of heterogeneity. So you can maybe have different uses of CPU and GPU resources. And even better is if you're working in maybe a DSL or something slightly higher level, where the programming environment can abstract or handle the data distribution for you. Another aspect, energy efficiency. As we know, most HPC applications so far have concentrated on, or optimizations have concentrated on time to solution, which to first order is a very reasonable way to try to reduce energy consumption. And then vendors have provided tools to improve on that. But there's more that can be done. For instance, I've seen some work where task-based programming models taking into account the knowledge about the upcoming workload because of dependencies and number of tasks and so on, knowing the degree of parallelism, you can then control how many processor cores to use to get the right trade-off between performance and energy, which may mean minimizing energy subject to achieving the maximum performance or close to it. And obviously, the importance of energy compared with time to solution might depend on the kind of job, whether it's an urgent job or so on. We also have some comments on post exascale, which similar-ish to many of the comments made before. So interoperability between HPC and AI, continue collaborating and HPC techniques into AI using AI-assisted tools, the digital continuum, the topics I mentioned before, and then the continued importance of high productivity, hiding machine complexity, transparent parallelism, and so on. And I forgot I put this in. So I just wanted to give a quick advert for a white paper that we did. It's a few years old now, but the fundamentals are still true. Talking about the benefits of task-based parallelism. I think many of the points I've got here I've said before, but if you want to read more details, this white paper is still very relevant. And then the key recommendations are here. I think I'm repeating myself as I read them out. Maybe I won't even read them out. Maybe I'll just leave them on the screen because I've said all these comments before. So I guess I'm done. That's it.
Thank you, Paul. I would like to remind everyone that you can ask questions in the question tool. Oh yeah, we've got a first question. So I will share my screen. Sorry, yeah, there it is. So you can see the questions in the chat. Gabrielle, copying them in the chat so everybody can see them. So we have a question from Marco Delia. Hi, how does the reconfigurable hardware FPGA enters in the picture for the programmer and at the system level?
Okay, I guess that's more a question for me.
Yeah, that's more like you, for
Programming
you,
environment.
Paula.
So I've been actually involved in a couple of projects that have dealt with that have worked with FPGAs. So there was a project EuroXR that I was really involved in, and the approach we took in this one was to essentially encapsulate work to go on the FPGA into tasks. So this is and essentially use maybe high-level synthesis. Actually, we used high-level synthesis to to generate the code for the FPGA, and then the runtime system would then execute tasks that have been mapped to the FPGA on the FPGA, and then the runtime system has to deal with the transfers between the FPGA memories and the programmers the CPU's memory. at the moment, or at least a couple of years back when we were working on this, it was quite challenging to use FPGAs. So one issue is just the length of time that it takes to do the place and route, making it very kind of very unproductive in terms of software development. But it's certainly very, very promising. I don't know if I answered the question or whether you had any other
Also,
questions.
also one follow-on comment to Paul is that we have discussed in detail this reconfigurable hardware and FPGAs in one of the working groups, which is a non-conventional architectures. So we have a webinar coming up on that. So Marco, you might want to keep your eyes open for that webinar as well. So there's going to be more discussion on that.
Okay, so we have more questions. So, question from Salem El Sayed for Philippe. You mentioned that observing I/O in the system would be helpful and could be used to train AI for prefetching. Could you comment on the complexity of doing so in an HPC system with mixed workloads, all hitting the storage system at the same time? So,
Yeah,
Philippe,
okay.
can you take this? Can you? Yeah, we can hear you.
Yeah, it's okay. Basically, there are two sides actually. First point is gathering data. So you have different way of doing that. You can have live props on every devices there that you fetch back and you put them the result byte to a central place, and you may use a syslog like architecture. Basically, it would not be syslog actually, but something looking like syslog. Basically, you may have a server concentrating the logs and props from the various systems they manage, and then send it back to a central place. And it's relatively small amount of data, so we don't need a specific network infrastructure to do that. It can be done via the network, the administration network. And once you have that large amount of data, you need to do some AI training on that. Basically, what we are looking for here is looking for outliers. And just a concrete example, you may want to investigate the whole data, and you may want to investigate just a subset of it. Two concrete examples. One is we gather that all of the logs from the smart provided by the disk, basically using smart, and we could identify that just before it fails, a disk was behaving in a certain way in the smart logs, and we could have a preventive detection of disks that will be about to fail. Another aspect is regarding application. Along with system-oriented logs, you may have more software-oriented logs, such as things you may be produced by Darshan. And those Darshan logs are to be investigating. So you can use AI and you can use other tools. And I am currently involved in a PhD work led by Henri Arène, where the student is trying to dig into Darshan traces in order to identify I/O patterns. So we have these different aspects. Basically, you can investigate the logs, the applications themselves. You can investigate the system, and you can gather everything in a big basket and for application are part of the system of the workload, and try to identify something interesting. But anyway, what is for the moment, what AI is good for is identifying outlier, basically points in the big picture that do not behave at the other one, and those are generally things that can help to identify weird behavior or misbehavior or system about to fail or this kind of stuff.
Thank you, Philippe. We have another question from Hans Christian Hopper.
Oh,
Hi, Hans Christian, by the
hello,
way.
Hans-Christian.
So, so it's for Philippe again. Where is additional work needed most? New storage systems or the integration and support of existing storage systems in HPC stacks and systems?
Well, I would say everywhere. Actually, you definitely need to enroll those new technology within, and you need to adapt the existing software so that you can deal with them. So it's so those two aspects are two sides of two sides of the same coin. You cannot have one without the other. You need, if you have new systems, you have to need the software to build the software for that, and new software, new feature, new like power management, like bottleneck detection and bottleneck resolution. You can address that by introducing new technology. So you cannot have one without the other.
Okay, good. We still have a couple of minutes for more questions. Do we have more questions coming in? No, I don't see any. Paul, Philippe, Sai, did any of you want to add anything to this or
Uh,
no?
Thank you for
Nothing.
inviting us to
Oh,
the group.
well,
It's always
thank
very
you for
nice to.
speaking.
I think just one comment is we can request our attendees to keep track of upcoming webinars on the different subjects. So it all helps to put a holistic picture of the entire HPC ecosystem and the HPC stack. So just stay tuned.
Yeah, the SRA and 8 white papers to this day are available on our website. So you see, I have put the link to our website. I mean, go visit it and have a look at the different white papers that are already available, and more are coming. So I think we can close now. So I would like to thank very much Paul and Philippe and Sai, of course, for being here today and sharing their work with us. As we already mentioned, we are going to organize more webinars about our SRA 6 and sorry, and its white papers. And the next one is at the end of February. It's about system software and non-conventional architectures. So as usual, I do send an email to all our webinar attendees to give them the new dates, but you can just go to our website and register. And thank you to Gabriela for sharing the questions because it's a great help. It's difficult to run everything at the same time. So bye-bye, everyone. I hope to see you at the end of February at our next webinar. Bye-bye.
Okay.
Bye
So
then.
thank
Bye-bye.
you. See you everyone. Bye.